Hi, I'm Antonio Sala. In this video we are going to discuss the equations of the movement of a point in planar movement, but we will use the so-called intrinsic coordinates. What are they? Well, basically when you drive a car, you drive 100 kilometers per hour, 60 miles per hour, and your body feels accelerations or braking forces in the, say, forward-backward direction, being forward, the direction of your car's movement, or you also perceive accelerations when cornering a curve. So somehow the important things you feel while driving happen either along the trajectory you are following or across it. You don't mind where north, south, east, west, or in which village you are when you are facing a curve at high speed. Likewise, an airplane pilot and the sensors of the airplane will usually measure things in what's called the body frame, something that it's moving with the body, except weight. Weight points always downwards, but okay. The thing is that the reference system that moves with you is called intrinsic reference frame, and in this video we'll discuss the equations of movement in such a frame. Of course, as it's moving, then it will not be an inertial reference frame, so that's why we need to explain some tweaks in order to correctly express the dynamics equations. In this video we will just discuss the movement of a point mass. The movement of a rigid body needs additional equations. We'll discuss it later on in the conclusions. So the first idea we are going to define is the tangent vector. We will assume that our velocity vector, if we are following a given trajectory, this will be the velocity vector, and then the unit vector describing the direction of movement will be called capital T, tangent vector. It will have an angle with, say, the horizontal or north-south or whatever thing, theta. This angle will be an absolute angle, the compass, for instance, will give me the reference axis for that. In this case, theta will be negative because we will consider positive in the anti-clockwise direction. The thing is that we will have this tangent vector t modulus 1, and then the actual speed will be such tangent vector times some scalar number, nu in this case, that will give me the actual speedometer reading in your car, let's say. So velocity vector will be modulus times a unit vector t, whose components will be cosinus and sinus of this angle theta, the angle that the trajectory is making with respect to a north-south, let's say, reference axis. Nu, the modulus of the speed, is also named as the speed along the trajectory, the arc length traveled per unit time in the geometry of curves. We will assume positive speed. Okay, we will not consider maneuvers in which this t vector suddenly changes direction in order for everything to be smooth and being able to give differential equations. Also, in pure geometry of the curves, usually it is assumed that the speed is unity when defining some normalized curvature and other geometric magnitudes independent of the speed in which the curve is traversed, in the sense that there is something about how this curve bends and the accelerations and forces needed to actually follow this path will depend on the speed we are negotiating that curves. So one thing will be geometry, speed-independent definitions, and other thing will be physics and dynamics with some accelerations, force, etc. Good. Once we have the tangent vector, we will define the normal vector. Our first definition, this will be the trajectory and the tangent vector. Then we will compute the time derivative of the tangent vector, and if the tangent vector is, cosinus and sinus of the given angle to be a unit vector, then if the angle changes with time, because of course the orientation changes with time, we will apply chain rule and say that the time derivative of the tangent vector will be minus sinus, comma, cosine times the derivative of theta. Here we have it, the sort of angular speed of the trajectory. And then this vector, we will call it normal. Well, normal to the port side in a ship, to your left-hand side when you are driving, in a counterclockwise 90 degrees turn. So this will be our normal left. You can check that indeed this minus sinus and cosinus corresponds to the coordinates of a vector which has been rotated 90 degrees in anti-clockwise sense with respect to this cosinus sinus. So good. This will be our normal left. But in differential geometry, what it's usually called a normal, Frenet normal vector, verifies this thing. Instead of taking the time derivative of theta, which can be positive or negative, well, the thing is that the usual definition of the normal vector will be when the trajectory is turning clockwise. Normal vector will be defined to be orthogonal in clockwise rotation with respect to the tangent, and in here, in which the trajectory is rotating in anti-clockwise direction, then the normal is the one in anti-clockwise. So this is equal to our normal left, but in this case, this normal will be minus our normal left. So in planar curves, the angular velocity, let's say, will be always considered without its sign. Curvature will be always positive, let's say, and it's the normal vector, the one which will change sign. However, in next slides, in order to avoid absolute values, we will keep our normal left to write the differential equations of the dynamics, but it's just a matter of sign conventions. So, to end up, once we have the tangent and normal vectors, or normal left in our case, we will have what is called the intrinsic coordinate basis, a coordinate basis that moves with the point and turns according to the curvature of the trajectory being followed. And the normal vector changes sign at inflection points in the trajectory when we change from turning, let's say, anti-clockwise to clockwise. So once we have defined our intrinsic reference frame, if we are doing dynamics, forces, we need accelerations. So we will define acceleration as the time derivative of the velocity vector. And of course, that will be also a vector. And we will compute the time derivative of this product using the product rule. The derivative of the first product term, nu, times vector t plus nu, sorry for the erratum, times the derivative of vector t. This fragment will be kept unchanged here, and the derivative of t will be either this thing or this absolute value thing. So we will replace it in the acceleration formula, giving either this or this expression, depending on which normal definition we are using. At the end, this is the acceleration vector, or this thing, and its component in the tangent direction will be called tangential acceleration. So this is the tangential acceleration, the time derivative of your speedometer reading, and the component in the normal direction will be called normal acceleration, either in an signed normal acceleration or in an always positive normal acceleration, given by one of those two expressions. This is the one with sign, this is the one without sign, always positive, and the things that we will have changes of sign will be the n vector. But okay, these are the accelerations in tangential and normal directions. So in order to end the presentation of the dynamics, we will need the forces. So if we assume, for instance, constant mass, then this is Newton's law. Acceleration is proportional to forces, and the proportionality constant is mass. So we will replace acceleration by this, and we will have the equations of the dynamics under constant mass assumption. Note that, for instance, in some rockets that burn fuel very rapidly, this constant mass stuff may need modifications, but we are keeping things simple for the moment being. So under constant mass, if we project the force over tangential and normal directions, or normal left directions, then replacing what we obtained here, we obtain these equations for the tangential acceleration and tangential force, and this equation for the normal acceleration and normal force. So these two equations give me the derivatives of the linear speed nu and the angular velocity d theta dt. And this is the main result of this video. The equations of dynamics in intrinsic coordinates are expressed like this. Indeed, a reminder on why we needed the derivations up to this point is because if we had constant t and constant nl, then Newton's law will be that the time derivative of the speed in the t direction will be force divided by mass, and similarly the time derivative of the normal component of the speed will be force divided by mass. But the second equation in particular is wrong, because the component of the speed in the normal direction is 0 by definition, so it will be its derivative. So we cannot write this because the reference system is moving. So this slide, you should forget that you have seen these equations, because the reference frame is not inertial, it's turning and accelerating. So the correct way to write the dynamics equations is the one in this slide. As a last remark, if we are moving with this velocity in direction theta, then of course the velocity in the x-coordinate will be nu times cosine of theta, and likewise nu times the sinus will be the velocity in the y-coordinate. So we may have these two position equations, which if I integrate will give me the position in absolute coordinates, let's say those given by a GPS. So we have the bottom two equations telling me the accelerations in intrinsic coordinates, and the top two equations will tell me how to compute the absolute positions from the accelerations at the bottom. So this will be the fourth order dynamics of a point mass, in which accelerations are measured in what's called the path reference frame. So let us conclude. In this video, we have derived this fourth order representation of the dynamics of a point subject to forces. Of course, these are equivalent to this fourth order representation of such a dynamics in an inertial reference frame xy. But if we take the so-called path reference frame, at least for forces, then we end up having these equations that may be useful in vehicle or aircraft dynamics. However, when discussing vehicle dynamics, we may realize that if the moment of inertia is not negligible, the aircraft or the car, whatever, may not be aligned with the actual path reference frame. This is a simplification, and the whole study maybe needs a minimum of 3 reference frames and rotations between them, what we call the inertial frame the GPS coordinates of my vehicle, the body frame, which is the orientations of my car or my airplane, and the path frame, which is the one we have been discussing in this video. Indeed, for instance, in an airplane case, we may have an airplane descending to land in a runway in which the path frame points in this downward direction, but the plane is shifted a given angle of attack, alpha, with respect to the path frame, because we want to touch with the tail landing gear when we hit the runway. So we cannot assume that body frame and path frames are always coincident, but as I said, we are in a first approach to the problem of vehicle dynamics. Also, when we are describing the equations of this kind of maneuvers, we can realize that the velocity vector points almost perpendicularly in this case to the body frame. So again, the equations we have discussed in this video are just the 2 degree of freedom point mass equations, path frame, and need to be expanded to cover the whole case of rigid body in planar dynamics or an aircraft in a whole 6 degree of freedom movement, which of course are not the topic of this material. So we end here. Thanks for watching.